This app is also about multiple linear regression, but in this case, first of all, we don't have interaction terms, so we have only independent contributions from two predictors, x1 and x2. You can still think about, for example, temperature and time of reaction. And then we also have data, the real data, right? So what you see as the blue points here, it's my sample, which are taken randomly from population. And then you can see that these gray points is just the same points that just in x1, x2 place. So you can see the relationship between x1 and x2 better, right? And then this plane, it's actually a multiple linear regression model that is fitted. Yeah? The two equations you see here, the first equation, it's our expected values. It's theoretical values that I use to generate this data. And this is the fitted values. And then you can see that in this case, the fitted values are pretty close to the expected values. So in this case, we have a very good agreement between the fitted model and the theoretical model, the real model. Yeah. Here you have some controls that you can change. And these controls mostly influence the sample. You can see we can change sample size. We can change fitting error. It's how well model can fit. You can see we have a pretty low fitting error. You can see where points are lying exactly, almost exactly on the plane. And then you can make it large, and then you can see that the points are a little bit more spread from the plane. So this is a large fitting error. And then you can also change the correlation between x1 and x2. And this is actually what this app is for, to investigate how correlation between predictors influence the quality of your model. Let's start with best sample. So we have no correlation, we have low fitting error, and we have relatively large sample size, which is 30, right? So you can see we have three unknowns. We have three regression coefficients that we need to estimate by making the fit, by using the linear square solution. And then you can see every time I take a new sample, you can see that these fitted values are a little bit different from the real one, from the theoretical one, but they are pretty close. You can also look at this plot. The gray bar is the theoretical coefficient. The purple or violet point, it's a current regression. And then you will also later see some gray points, which are different samples, the fitted regression coefficients for different samples. So in this case, you can see that this point varies very, very little. So we have a very, very good fit. If I change sample size to 10, and then start doing this, you can still see the fit pretty good, but maybe this spread is a little bit larger, but not we don't see it clearly. Of course, if you make a larger fitting error, the uncertainty will also be larger. So now if I start taking many, many, many samples, you can see indeed I have kind of a bigger uncertainty here, right? And then if I, for example, change sample size to 30, and then look, you still have some uncertainty. So the fitting error, of course, influence the uncertainty for the fitted coefficients, but still pretty good match. So the uncertainty is relatively small comparing to the magnitude of the coefficient. So we can say that we have a pretty good model even when fitting error is large. But you remember that one of the requirements for multiple linear regression is that your x and x2 and x1 values, your predictors, are independent. So it means that there is no correlation between the predictors. And this is what we have here. Indeed, the correlation is very small. What happens if you have a correlation? So for example, if you have a low correlation, yeah? So low correlation is approximately 0.3. So if I take a lot of samples, you can see it's still pretty good fit, but you can notice that the variation of the coefficients is getting larger. If I have medium correlation, you can see it's getting even larger. I didn't change the sample size. I didn't change the sampling error, but you can see even with medium correlation, it's getting larger. And if I have a high correlation, you can clearly see the correlation pattern now, right? So you can clearly see this linear relationship between these x1 and x2 values. Now we are in trouble. Look at that. Look at this model, how far this model is from the reality, right? So you can see that this coefficient is twice larger and this coefficient is several times smaller than the reality. And if I take a lot of samples, although the sample size is relatively large, it's 30, right? It's 10 times larger than I actually need, minimum. Look how big the variation of the regression coefficient. So our model is very unstable now. So this is why the correlation is a problem, especially if you have a high or medium correlation for the multiple linear regression model. So your model becomes very unstable. And If I change the sample size, for example, make it smaller, it makes it even worse. So you can see strange things. Sometimes you actually cannot even fit the model, so you'll get an error because sometimes it's mathematically impossible to fit these points with MLR model. Okay. So that's why we try to avoid correlation, and that's why it's very important that you design your experiment to have no correlation between your predictors. For example, by using full factorial or fractional factorial design, or if you collect the data, make sure that your data covers the predictor space evenly, so you don't have any significant, any strong correlations between X1 and X2. But if you have, for example, low correlation, even if your sample size is small and fitting error is large, you have, of course, uncertainty, but it's relatively small, so it doesn't influence your quality of the fit much. So, but the medium and high correlation can be really a problem.